This is the solution for day 8 of the Advent of Code 2022 in Rust, and today we're building tree houses. We're getting given a grid of trees. Each tree has a height. We're looking for those trees that can't be seen from outside the forest. So we're only considering rows and columns through the forest, and we're looking for any tree that's taller than the tree we're considering, and that's enough to block the view from outside the forest. So we're given some examples here, but if we just have a look at the grid, for example, we could pick out this number 5 here. So we can see that on the left there's another 5. That's tall enough to make us invisible from the left. But on the right we've got trees of height 1 and 2, so we would be visible from outside the forest on the right. So the first problem is to find how many trees are visible from outside the grid for our input. So let's get started. I've kicked us off by loading up the input file and converting it to a vector of strings. So let's have a look at the format of that file. So each line of text in the file is giving us a row in the forest, and then working down the file we've got our columns. So we'll think about it like a grid where we've got an origin at the top left at 0, 0, that's our first character, and then we'll treat going along through each line as increasing the X position and going down through the file as increasing the Y position. So treating it as a grid, and we don't need to check the first row, the last row, the first column or the last column, because those are all forming the border of the forest. They're all the last tree on each side, and those must be visible by definition. So we only need to check the inner part of the forest. So first thing we want to do is get the dimensions of our forest. So we can get the width of the forest by checking how long one line is. And then we can check the height of the forest by checking how many lines we've got. Then we want to have a grid of numbers. So let's convert our text input to be a list of numbers, or a grid of numbers. So lines, iterate, and map. And then each line is a row, so we'll split that up into characters and map it. And then each individual character is a small number, so we know that it's going to be valid ASCII, so we can just cast it straight to U8. Collect and collect. And that's our forest, which will be a vector of vectors of U8, where the inner vectors are each row and the outer vectors are the set of rows or the columns, however you want to think about it. So let's run through those. So for the Y position, in 1 through width -1. So that's where we're dealing with not checking the last values on each row and column, or first and last values on each row and column, by moving in 1 from the 0 start and back 1 from the width end. And we'll do the same with the X values. There we go. Now we can grab our height for our current tree that we're checking. And we do Y first, because we're running along each row before we move down through the Y values. It doesn't really matter what order we do that in, as long as we're consistent. So then we're looking for any tree on the same row or on the same column that is at least as tall as us. So that's enough to give us cover. So let's figure out how we set that condition up. So we can do, for something that's on the same row to the left of us, we can stay in the same Y position, same distance down the grid, and then we can check everything from the start through to our current tree, and the upper bound here is exclusive, so we're not checking the current tree. We can iterate that, and we can check if any of those trees is at least as big as our height. So that checks to the left. We can also check to the right. So if forest, same Y position, starting at X plus 1, because the lower bound is inclusive. Don't need an upper bound, we'll run to the end of the row, iterate through it, and check if any of the trees are at least as tall as us. Then we can not be seen on that row. So that's the row condition. Let's start keeping track of our possible trees. to build a treehouse. So if this condition is true, then this is a possible tree. Let's go ahead and print out the result. Excellent. So the next thing to check then is whether we can be seen on the column. So we can do something similar to this. So perhaps slightly unintuitive to look at. So with this, it kind of makes sense. We're taking one vector out of our set of vectors and selecting a range from it. But we can actually do exactly the same thing, or something very similar the other way around. So let's go for, if we save this, will it format it? Yeah, that makes it easier to work with. So forest. We can select out a range on the Y position. So we'll select out a range of columns to work with, or sorry, we'll select out a range of rows to work with, and then we'll iterate through those, and then we'll check if any, and this time we're being given a row, not a single value. So we'll have to index the row at the current X position. And then we can check if that is greater than or equal to H. And then we can do the same thing for the bottom beneath where our current position is. So forest from Y plus 1 up to the end, and iterate and check if anything in there is taller than us or the same size. H. So that should do it. Let's run that and see what it says. So I'll kick it off with cargo run. And it's saying 9,409. So it's running, but that seems a little high to me. It wouldn't take very much for their condition not to be met. I'd expect that number to be lower, even though we have quite a big grid. Let's just give that solution a check. Okay, so what doesn't look quite right? So we've been careful about our boundary conditions. We're working in the interior of the forest only. We're consistently using Y as the first index to select the row, and then X to select the column in that row. So that looks good. We've been careful about exclusive ranges on the right and on the left, and the same for the Y values. So that looks okay. And then we're checking if any of the trees gives us cover. But we're using an OR condition. That should be an AND condition. So that's what we're missing there. So that then calculates all of our possible trees, and then we've been asked to find out not the possible trees, but which trees are visible, how many trees are visible. So this isn't quite the right answer. We should be looking for visible trees, and we'll be doing width times height minus the value we've calculated. So that will give us visible trees. Let's run that and see how that does. Okay, we'll try it again. And that's saying 1,851. So that seems like a more reasonable number. Let's give that a go. So is it? Yes, excellent. So we can move on to part 2. So part 2 is asking us to solve a slightly different problem. So we're saying for each tree on the grid, how far can we see from it? So we can see as many short trees in front of us as we want, and as soon as we see a tree that is taller or the same height, we count that tree as a tree we can see, but we can't see anything behind it. So we want to go round in all 4 directions, so left, right, up and down, and take the distance we can see, which will always be at least 1 in every direction, and then, apart from on the edges where we'd have a distance of 0, and then we'll have to multiply those together, and that gives us a scenic score, which is a metric that is unique to this problem. So let's jump in and give that a go. Part 2 is still going to require us to run through our grid, so let's grab the code we use for that, and just get rid of the logic we use to look for hidden trees. And we're now trying to find a max scenic score. And there's no point considering the outsides of the grid still, because everything on the outside will have at least one 0 distance, because there's no trees on the left to look at, or right to look at when you're on the edges of the grid to the left and right. So we'd end up with a scenic score of 0 anyway, so there's no point calculating it, it won't be the max. So just the interior trees. So we can grab our height out, and then we're going to try searching in every direction outwards from our tree, looking for a tree that's the same height or taller. If we find that, we want to track the distance to it, and if we don't find one and we hit the edge of the grid, we still know how many trees we're looking over. So let's start by going left from our position. So we already know how to grab all of the things to our left, but we don't want to traverse it in order from left to right. We want to go right to left, going from our tree back towards the edge of the grid. So let's reverse the iterator. And then we want to track our position, so how far we travelled. So let's enumerate, and that will take our iterator and give us back a new one that has tuples, where the first element of the tuple is the index that it was into the iterator, and the second value is our height of the tree. Then we can find the first tree, throw away the position, grab the height, so where the height is greater than or equal to our height. So searching left to right, or sorry, right to left, looking for a tree that's at least as tall as us. So if that succeeds, that'll be a sum on the find, and will give us back a position, and we don't care about what the actual height was. So in that case, the number of trees we looked over is pos plus 1, because the enumerate gives us back a 0-based index. And otherwise, the number of trees we were looking over is the same as our current index. So if we were at index 2, then indexes 0 and 1 would be on our left, so it comes out at 2, which is our current index. So let's track our score as we go. Scenic score is 1, and we can multiply that onto there. Star equals. So multiply and assign. Then the next three cases are quite similar. So I'm going to go ahead and add those in, and then I will show you what I've done, and we can continue from there. The differences are subtle but important. So for the second bit, we want to search right from our current tree. And in that case, when we grab the values out of our vector, they'll already be in order, so we don't do a reverse here. The other difference is when we calculate the distance to the edge of the grid if we don't find a tree that's taller than us. So it's not x this time, it's how far from our current position do we have to go to the edge of the grid, so up to the width of the grid. And then similarly to what we did for the search for hidden trees, we select a range of rows and then index those rows with the current column position. But otherwise it's exactly the same, calculating the going up and the going down. We're just using y's instead of x's and selecting rows instead of columns initially, and that is that. So now that we've calculated our scenic score and we've got a max that we want to track on the outside, we'll update that max when we find a higher score. So if the scenic score is higher than max, then max scenic score gets assigned to scenic score, or the other way around, the current value of scenic score gets assigned to the max, Then when our loop finishes, we'll have gone through the entire grid, we'll have found our maximum, and we can print it out. Max scenic score. Alright, let's give that a test against the sample we were given and see if it gives us the right answer on the test solution. Okay, let's give that a run. And it's saying 16, but the answer from the website, from the problem, was 8. So we're slightly too high. Let's check what we've done. So given that we were off by exactly double the right answer, we're probably looking for something that's making us multiply by 2. So my best guess is that we're off on indexes. So I explained what was going on with the pos plus 1, and I'm pretty sure that's right. X should be correct, so if we've got a grid of width 4, we're currently at position 2. That would mean we have indexes 0 and 1 on our left, so we have 2 things on our left, so that works. So the only thing left then is this width minus x. So if we were at position 2 on a width 4 grid, the difference would be 2, but actually we're tree number 3. There's actually only 1 tree to our right. So this should be adjusted by 1, and the same with this one here. That should be adjusted by 1. So let's try that again. That should now give us a score of 8. And it does, good stuff. So let's try it on the full input and see what our answer comes back as. So 574080. Let's see if that's the right answer. Moment of truth then. Excellent, we got it right. So that's the end of day 8. Harder than it looked, but not nearly as difficult as yesterday. So I hope you're getting on well with the Advent of Code calendar, and I will see you tomorrow for day 9.